Okay.
So I really want to talk about trying to understand the Artin reciprocity theorem, or aspects of the Artin reciprocity theorem, which basically means to me that the classification of abelian extensions of number fields. And I really want to do that in the example where the number field that we're extending is the Gaussian field.
Okay.
And this is following up on things I was talking about, I guess, probably 2 weeks ago, but perhaps fixing some mistakes and just trying to understand things very concretely. Well, like I said, this is about the understanding the classification of abelian extensions of number fields, but that's just one way of putting it. There are many loosely equivalent ways of describing it as well. But that's kind of the way that I'm thinking about it at the moment.
Okay.
And
So I'd be curious what those other ones are. Should I not ask?
Well, no, you can ask. I mean, so one way that we've talked about is, you can talk about, you can think in terms of abelian extensions, or you can think in terms of torsors of abelian groups. And those classifying those things are very closely related to each other, almost equivalent.
I'm confused about that, but I should.
Yeah.
Oh, I shouldn't have asked. Okay, don't answer this, but
yeah,
I'm confused about why. Maybe the answer is no, but I'll say why or whether these torsors always come from field extensions, or as opposed to like some other kind of algebras. So
as opposed to some kind of algebras, what?
Yeah, so a field extension is some kind of algebra over a field.
Yeah.
I don't get why a torsor needs to be a field extension, and I think maybe you've said it doesn't.
Yeah, no, that's fine. That's fine. Yeah, no, that's just sloppiness on my part. But I mean, there's already enough sloppiness built into the way I stated it that I don't think that's a terrible.
Well, I'm not saying anything's terrible, but it's true that it doesn't need to be a field then.
Right. It's kind of like, it's very much equivalent to, you might have one person who studies the topos of G sets for some group G, maybe a finite abelian group, for example, like that. And some other person might just study the subgroups of G. And those subgroups, you can associate those with the transitive G sets. So one person is studying the transitive G sets, the other person is studying the G sets as a whole. But you can translate back and forth between those, and that's kind of the same thing that you were just talking about. You were talking about.
Well, sometime I want to understand how to translate between these things, which sounds like you think I already.
Well, but it is very straightforward. It's just applying the duality, the duality between algebra and geometry, applying it to what I was just saying about transitive G sets. It's kind of like the study of subgroups. And
what about torsors? Torsors sound transitive, but that's some weird levels.
Well, there's a whole bunch of level slips here, sliding along the long exact homotopy sequence, or not so long exact homotopy sequence. But let's see.
I mean, you could just tell me like a torsor of the sort that you're always talking about.
Yeah.
Is a field extension if and only if blank.
Well, again, I mean, I'm so not sure is exactly the right word.
Okay.
You know, you could think of the torso as a field extension with a little bit of extra structure or something like that.
Well, anyway, we don't have to talk
I
about
mean,
this
well,
now, but I'll never
I mean,
know what's going on until I know exactly the answer to this question sometime.
well, but you know, you could think of a torsor as a kind of, you know, when you would think of it from the philosophy of algebraic geometry, you can think of a torsor as a kind of principal fiber bundle. And when you and from that same philosophy, you can think of an extension field or an abelian extension field, for example. You can think of that as a kind of fiber bundle, perhaps not quite a principal fiber bundle. Well, in different circumstances, whatever, but right, they're both kinds of bundles, and they're close enough to being the same kinds of bundles that they're practically the same thing. I mean, you know, when you say an abelian extension field, you're actually sort of making, that's, you know, if you think of that as an extra structure, you think of the abelianness as an extra structure, and you're kind of making that bundle into this principal fiber bundle for that Galois group. And it's all just, you know, it's all this very geometric thinking about bundles, principal fiber bundles versus other kinds of bundles. And
it's not like principal fiber bundles versus, it's not like principal G bundles versus other G bundles here, because you're just working with torsors, right? So it's just about things that haven't yet been given the structure of this G action on the fibers versus ones that have.
I mean, the non-principal fiber bundles definitely are coming in here, but they're more coming in on the other side, probably. You know, the extension field side. But I mean, they're all of these things are fitting together in very straightforward geometric ways. You just have to translate it into the algebraic language by the usual duality between algebra and geometry.
Okay, so
and I might be, you know,
yeah,
committing all sorts of blunders of thinking or exposition or whatever in the process of doing this, but that's just, you know, my problem. You're supposed to see beyond that because it all does make sense.
Okay, well, anyway, at least you see that you're just sort of saying like, figure it out. It's not hard. Okay, which is okay. That's fine, because this guy didn't really want to derail the conversation.
Okay, right.
But you see that I can't.
I'm encouraging you that it is very easy to figure it out.
Yeah, right. Okay, so anyway, I need to figure it out then.
And it is worth talking about it some other time, but not right now. Right. Okay.
Okay. I'm not instantly getting it. It's all I'll register like. So.
Sure. But you know,
okay.
But much later you will instantly get. So there's a particular Galois group. I guess it's certainly a group, and if you squint at it the right way, you can construe it as a Galois group. There's a particular Galois group that I was talking about recently, which is sorry, let me try a different color here. Black. Okay. GL1 of I'll write G with an underbar for the Gaussian integers at the moment. Modulo 9. I think that's what I was talking about, and that's like 2 weeks ago, possibly, and that I want to talk about again today.
Okay.
And so first of all, you know, we've got this reasonably sized graph paper here. Let's you know, perhaps even before we start thinking about how to think of this as an interesting Galois group, let's just try to see it as a group here. So how does this work? Right, okay, again, we have the big issue here of do we think of the Gaussian integers as living in the centers of the squares, or do we think of them as living at the vertexes? I guess I'm thinking of them as being in the centers of the squares at the moment, because that way I can write labels inside the squares that might stand for these Gaussian integers or something like that. So this looks like a little 9x9 thing that we can sort of mentally roll up into a torus if we like. So I guess this is the real axis. Am I doing that right? And this is the image. Oh, luckily, okay. Sorry. Can I do this without getting myself too badly confused? Can I try to stick to standard conventions? So that's sort of the real axis, and this is the imaginary axis. Let's see.
Just speaking of conventions, are you
What?
writing speaking of conventions, are you writing the Gaussians on the crosshairs of this grid or in the holes?
I actually said that. You were totally blanking out when I had the.
Yeah, I was totally blanking out. Yeah.
I said I thought about it and I decided they're going in the holes.
Okay.
In the deep holes, which aren't very deep, but in the deep holes.
Okay.
Because that way I can write
yeah.
labels inside the square.
Okay. Right. Yeah. Okay. No, then you said standard conventions, and so I thought it was amusing. Okay. Yeah.
Right. That is not a non-standard convention, perhaps, but okay. Okay. So that was your basis of your complaint. Okay.
Well,
I guess you're right. That's right. Because now I'm saying the origin is like right there. And that's not very standard.
Yeah, that looks terrible, but it's okay. It's a good.
But it does remind me of mystical things where people have the center is off by 1 or something like that when you're working with root systems or something like that.
Yeah.
So okay, so there's 81 squares here, but those are not all in this group because those are not all right. So this is a quotient ring. And GL1 is an affine algebraic group that instructs us to take our commutative ring and take the invertible elements under multiplication. It's also called the multiplicative group. So we just have to find the invertible elements, and 9 is not, right? 9 is not a prime, right? So it's not, so there's more than one non-invertible element. It's not just 0. Is easy to find where the non-invertible elements are, so we can put some sort of mark in them. So those will, okay, so maybe I could just put zeros there, or circles. Don't necessarily think that's a 0, but I'll put circles where all the, maybe for the 0 divisors or something like that. So where are they all? Are they like, is this where they are?
The non-primes?
The non-invertibles
Non-invertibles.
in this finite group. So right, in this finite multiplicative monoid or whatever. So there's 81 elements.
Yep.
And there's 9 of these 0 divisors or whatever.
Yep.
And I don't know. It sounds like I'm sloppily equating 0 divisor with non-invertible. No, maybe that's like an exact synonym, actually.
Yeah.
What?
Yep.
Okay, and so that leaves 81 minus 9 equals 72. Is that correct? So this is a 72 element group. So a 72 element group, 72 element abelian group. This is a 72 element abelian group. And a 72 element abelian group canonically splits as a direct sum of an 8 element group and a 9 element group. Yeah. And can you see those subgroups in this picture? The 8 element subgroup and the 9 element subgroup.
So there are a bunch of 8 element subgroups, like horizontally and vertically and diagonally. Unless I'm really confused.
You're probably right, but I'm thinking about things to draw here. I didn't catch everything you said. Can you say it again?
Well, I was partially wrong, but so the real numbers. So on that horizontal axis, they're an 8 element subgroup, multiplicative subgroup, I guess.
Say it again. On the real what?
On the real axis, the ones without zeros in them, that should be an 8 element subgroup.
No, I don't think so. I think that's a 6 element subgroup.
Oh wow, I couldn't even count. Okay.
Right.
Oh boy, well then, so that's like some weird mixture of your.
Right. It might be a little bit easier to find the 9 element subgroup than the 8 element subgroup.
I don't know.
Well, I mean, you see a 9 of something in here, right? I mean, this is right. Okay. So okay. Okay. Yeah. Okay.
Non-subgroup. Yeah.
Let me see. Let me first of all, let me erase what I wrote there. Let me try to write it a little more systematically. So we have a short exact sequence here. So what is it? This is a sort of short exact sequence that we've mentioned before. GL1 Gaussian integers mod 9 projects down to the multiplicative group, the GL1 of the Gaussian integers mod 3. And then there's a kernel, which is, I think, the additive group.
Oh, okay.
Of what? Maybe I should put a question mark here, but I think it's true because we've run into this before and it seems to be true here. GL, no, sorry, what am I doing? Sorry. Not GL, just G mod 3. And is that clear? That's a 9 there. So there's a short exact sequence here. And
sorry, yeah, we have talked about this before. Did you say that GL1 G mod 9 is right? It's right. Okay, yeah. I just have to say it's not the affine group of the affine line G mod 3. I mean, because it's a
that's right. That's right. That's right. Because that would be non-abelian, right?
Right. Yeah. So it's
yeah. Right. So I wish I did understand this short exact sequence better, but I think it's showing up here. But okay, but I wrote question marks there to partially indicate that I'm not even certain it's working exactly like this, but also the question marks there are partially to indicate that I'm asking you to think about this, look at these pictures and see if I'm right in saying that this is how this short exact sequence goes there. So like I say, I think this 72 thing here, I think this is 8 over here.
What?
Yellow
1, G mod 3? Oh, G mod 3. Ah, okay, yeah, sorry. Yeah.
Yes, because 3, unlike 9, 3 is a prime. So that's a prime ideal. So that's a quotient field. The quotient ring is a field. So there's just one zero divisor, which is 0.
Yep.
I think this is 9. Well, right, one encouraging thing is that, right, this makes sense. The additive group of.
Well, yeah. Yep, yeah, the numbers are right. Yep.
Okay. And the additive group, right, there's some numerology at least that's making sense here. But right, we're sort of trying to check that this numerology is better than just numerology, that it's actually a categorification of something going on here. The categorification of 9 times 8 equals 72. And well, let's see. So this is a short exact sequence, but I seem to be claiming, right, that it canonically splits. So what does that mean? That means that there's a section here, canonical section here. Why should there be a canonical section here? Well, it's probably, I don't know. So let's see. Let me try blue. Well, okay. I'll tell you. So, okay. So the additive thing is an honest subgroup. An honest subgroup of this multiplicative group. So you should just be able to see it as some 9-element subset. So can you figure out where it is? I'll draw it in blue or something like that. So it's got to include the identity element, but where are the other? Right, did I do that right? That's the identity element. That's 1. The multiplicative identity is 1, but where are the other 8? Where's this 9-element subset?
I don't know. I mean, a stupid guess is just you draw the dots to the right of the dots that you.
Sure. You got to be more ready and willing to make stupid guesses because they're always right.
Oh, if I knew that they were always right, I would. Yeah. Yeah. No, I mean, anyway.
Yeah. So that is. So I don't know if let's see. Is there a thing here? How do you? Add a pen. Can I get a yellow? Where's the yellow? I don't know. That doesn't look like yellow to me.
Claims it's yellow. It looks orange to me, but yeah.
Yeah, I don't like that.
I've discovered that people have different opinions about what yellow is, but yeah.
That's interesting. I was kind of hoping that blue and yellow would, add up to green here, but maybe it's not going to work. It didn't work very well. So I'll just, make it half blue and half. Well, that's a little bit. What is it doing? Is it doing? Oh, okay. It's supposed to be thin. Okay. And did I do that right now? Okay, now let's see if it comes out. Okay, so that one's both blue and yellow. But can you make any guesses about where the rest of the yellows are? So there should be 7 more yellows somewhere. Yeah, what am I trying to say? I mean, right, it's supposed to be like the multiplicative group of where the hell is it? Well, right, we could pick like there are all sorts of random sections that you can pick, but I guess there's just one, right? I mean, one random section would be like those 8 elements right there. That's a section of this, that's a choice of representatives of the congruence classes mod 3. But it's apparent, I don't think, that's probably not going to be the correct one, the one that actually that you allegedly get canonically. Well, so why do we get, is it clear why we get this canonical thing? I was tempted to say something about Chinese remainder theorem or something that's going to give us this canonical thing here, but maybe that's overkill or underkill or something like that. I don't know, but I'm pretty sure there should be a canonical one, and evidently this is not it, because I don't think that's closed under multiplication. But I think what it ends up being, and I don't think I used any particular magic conceptual thing to figure this out, is so where is it? It's like, it's supposed to be 8 elements. Where the hell could it be? I think it's this one and this one and this one, but what is this one? That's like up here. And this one, but I guess that's over here. And I think it's there and there. Is that right? No, that can't be right. Let me try again. Maybe. Does this seem at all plausible? Let's see. So, right. So first of all, it's got the 4 cardinal elements, 1 I, -1, and -I. And then it's got this element. So it just must be, what I get when I subject this thing. So right, it should be down here or something like that. So I guess it's there. And where is it? Where is it? Right, it's supposed to be very nice and symmetrical when you're looking at this rolled up torus. So am I doing this right? Again, try to catch me in mistakes here. Right, okay, that makes sense right there. So there's this element and there's this one. I'm really having trouble believing that that's correct, but
so where did 2 + 2i come from?
I probably cheated and used Mathematica to calculate it for me. I mean, I think so what is this square of 2 + 2i? So I think, so there's these 4 cardinal points, and then we're looking for another 4 points, and they should be right. It's supposed to be an 8-element cyclic group.
Yep.
So the 4 cardinal points must be the even ones, and we're looking for the 4 odd ones. So we're looking for the square roots of the 4 cardinal things. So is it true? Yes, if I take 2 + 2i and I square it.
It's imaginary. It's a positive imaginary axis.
And it's 8i.
8i, okay. Yeah.
So, and yeah, I've got it right there, 8i. Yes, you square this one and you get this one. And now I'm trying to figure out where the other ones are. I mean, this one looks so different from the way this one does, but couldn't that be right there? Let's see. I mean, it's actually, you know, 2 plus 2i, 2 minus 2i, minus 2. So did I do that right? This is 2 plus 2i. This is 2 minus 2i. This is minus 2 plus 2i, and this is minus 2 minus 2i or something like that. So I guess, yeah, I guess somehow I somehow was expecting the, you know, the placement between the yellows and the blues to be more balanced or something like that, but apparently this is the way it is. Yeah. So, okay, so what's going on here? So, right, by some general principle that I'm struggling to articulate, I mean, the fact that this or perhaps some quotient group of this is going to act as a Galois group, an abelian Galois group for you know, for certain abelian extensions of the Gaussian field. And so let's see. So we're gonna have what? We're gonna have let's see. Okay, so we've got that 8. How does this work? 8 element group. See, I mean, when we were talking about this two weeks ago, there was another subgroup that we were talking about, and it was a 12 element group. And what was that 12 element group? It was like, I think it was, you know, I'll put a red circle around it or something like that. I think it was these 4 points. But then there was another thing in there, and I think it was 3 plus 9. Let me see if I can find this picture in here, in my notebook. I think it's like 3 plus I, yeah. So where's 3 plus I? Right there. And then I think it would be like, wow, this is weird. Like this. And this. And this. And this. And this and this. So that's some weird 12 element subgroup. Okay, but that's actually a very important subgroup. So let me tell you what that is. That is the red equals the that the norm is congruent to 1 mod 9, I think. Is that right? Right, because this, yes. And what this means is that this is the Galois correspondence splitting congruence pattern for the extension of the Gaussian field where you put in all the primitive ninth roots of unity. Okay, wait, let's think about this and see if this makes sense numerologically, okay? So if you put in the primitive ninth roots of unity, then that's a 6th degree extension, right? That's a 6th degree of abelian, well, it's a 6th degree abelian extension originally of the rational field.
I'll take your word for it.
Well, no, but it's
quadratic extension gives you the cube roots of unity. Okay, and then I guess you're claiming that then you need a cubic extension of that to get the ninth.
Well, I mean, the Euler, remember, you miscalculated the Euler totient of 9 as being 8 earlier because you were counting the.
I don't know what I was doing.
Well, I mean, but there were just 6 things relatively prime to 9. There's not 8 things relatively prime to 9. And that's I think the Euler totient. Isn't that what it's called? The Euler totient of 9 is those 6 elements in that multiplicative group. And you know, so those are the 6 primitive roots of primitive ninth roots of unity. So the 9th cyclotomic field is a 6th degree extension. Yeah, because right, you could say that this 9th cyclotomic polynomial, the cyclotomic polynomial for the 9th primitive ninth roots of unity is a 6th degree polynomial. So that's a 6th degree equation. So so if we've got a 72 element group here, then the primes that split with respect to this 6th degree extension should belong to these congruence classes that, you know, are sort of density 1/6 in the group. So that would be, you know, 72 out of 6 equals 12. So there should be a 12 element subgroup, and it is this red subgroup. And it's distinguished by the fact that the norm of these Gaussian integers is equal to 1 modulo 9. And that makes sense because, you know, if you go back to the ordinary integers and you look at the splitting congruence pattern for the splitting congruence pattern for the
Gaussians?
No, for the ninth primitive ninth roots of unity, that is just equal to that the prime itself should be congruent to 1 modulo 9. And then when we say norm here, we mean the Gaussian norm, which is like, I guess, right, it's the product of the 2 conjugates. So it's like the square of the usual
norm.
Yeah. That's not my fault. I think that there's that ambiguity.
No, definitely not your fault. Yeah, I hate that.
Lots of things are my fault, but that's not my fault.
Yeah.
So, you know, I'm claiming that this is all hanging together. That, you know, this is, you know, the norm being equal to being congruent to 1 modulo 9. That's, you know, sort of the right thing to do to see what happens when you add the primitive ninth roots of unity to the Gaussian field. Because when we added them to the rational field, we just took that the number itself is congruent to 1 by 9. But now we're taking that the Gaussian norm is congruent to 1 mod 9. And that's this red stuff here. And that, like I say, that's a 12 element subgroup. So it's like density 1/6. And that's exactly what you need for a 6th degree extension. So a bunch of things here are fitting together in a way that allows me to, you know, think to myself that I'm intuitively understanding a lot of this. But it's, you know, a lot of it is very gritty and looking at this. So the reason the main reason I'm getting really involved in analyzing all these subgroups of this general linear group, which is sort of giving us like an abelian Galois group here. The reason why I'm trying to understand, trying to study this in such intense detail is that I think I originally had a conjecture that there was just this one single cubic, one single abelian cubic extension of the Gauss of what am I trying to say? That originally I was thinking that there was just one index 3 subgroup here. Well, okay, so the red thing is actually an index 6 subgroup. The red thing is actually an index 6 subgroup, but there's an associated index 3 subgroup, which is just kind of, I forget exactly what it is, but it has to do with whether you take there's this extension field that you get by adjoining the primitive 9th roots of unity, and that's a 6th degree extension. But there's also an associated cubic extension inside of that. And that's the extension that you get by not actually taking the primitive 9th roots of unity themselves, but just taking the coordinates of those with respect to a basis given by the primitive 3rd roots of unity. So it's like we're trying to skip past the primitive 3rd roots of unity and not include those, but just include the stuff that would give us the primitive 9th roots of unity if we had the primitive 3rd roots of unity. So that's what this index 3 subgroup is. And it's just like, it includes this red thing, and there must be 12 more, and I don't quite see where they are at the moment, but it's actually easy to figure out. But the big problem that I hadn't realized was that there's another index 3 subgroup of this abelian group, and that's and very stupidly that surprised me, and very stupidly on my part to not have realized that was going to happen, because somehow I think what happened, I try to come up with an excuse for how I made some stupid mistake here. I think I was stupidly expecting this group to be cyclic. And that's just clearly not the case. And right, the reason it's not cyclic is because this thing over here is not cyclic. Right? This is Z mod 3 squared. So it's not a cyclic group. And that's preventing the whole group from being a cyclic group. So, right, do you know what I'm saying? If this were a cyclic group, then we'd only have, if it were a cyclic group, we'd have a unique index 3 subgroup. And then there would be, a corresponding unique abelian cubic extension of the Gaussian field. And I would know exactly what that one was, because I'm expecting, right? I'm expecting there to be this abelian cubic extension corresponding to taking the formal primitive 9th roots of unity. So, I thought I had everything lined up so that I knew exactly which extension was corresponding to this index 3 subgroup here. And I was working with that, and then I ran into calculational paradoxes And, I was really confused for like more than a week. And I finally realized that the stupid mistake I was making was that there's not just a unique index 3 subgroup here. You don't get, and it's because I was stupidly thinking that there was that this whole subgroup was, that this whole group was cyclic, and it's not. But again, to try to give somewhat of an excuse, we have this pattern that seems to, I don't think we're sure yet how general this pattern that we have of when you have a prime power here and you get this short exact sequence where the quotient is multiplicative and the kernel is additive. That's a sort of pattern that we've run into. And we can sort of see it operating here with, you can see this additive subgroup in here of the blues. So there's something that's very simple here. But when I had run into this pattern before, it was when I was working over the ordinary integers. And I was working over the ordinary integers, the additive group was cyclic. And now, of course, I'm working over the Gaussian integers, and the additive group is not cyclic. And that was my stupid mistake. I just, didn't realize the obvious fact that because the Gaussian additive things are not cyclic, that prevents these from being cyclic. So that means that there are more abelian cubic extensions of the Gaussian field than I had reckoned with. And so
you get one of them from the other ones by somehow multiplying it by I, or somehow using I to twist it around.
That's a great question. That's my big puzzle for the moment. I mean, I several times I made a guess very similar to what you just said, that somehow it's gonna.
Yeah,
I was thinking like we've got.
It is true that if you have an additive subgroup of Gaussian's mod 3,
you
can multiply all the elements of that by I think that makes sense. And then you get another additive subgroup.
Yes. So, so the red subgroup in here. Right, there's this funny overlap between the red subgroup and the blue subgroup, and that's this subgroup over here. And that's like related to what you're talking about, I think, here. And so like there's another one over here, which is like what you just said, I think, that you can just multiply by I. And right, so I think this is the one that's giving us this is giving us, again, I'm being sloppy here, but it has something to do with this. This one is like, let's see, this is the one that was apparently giving us. Right, the red one that intersects the blues in this subgroup is the one that's giving us the formal primitive cube roots of 9. Actually, the red one is just right. The red one is just 12 elements, so it's actually giving us not just the formal primitive 9th roots of unity. Did I put this is can't decide whether it's good or bad that I have the recording to go back to and see if I said everything wrong. But I meant to say that, yeah, this red thing is corresponding to the primitive ninth roots of unity. And but then there's this different red thing that would intersect the blues in this thing. I mean, this, I'm or don't call it red, there's some other color, purple or something, that would intersect in here. And that would be applying your principle of getting this, just multiplying by I and the additive thing, something like that. So what would that correspond to? What would that correspond to? And I if I understand your guess, I made similar guesses, but I just can't see how those guesses would work. I mean, what am I trying to say? I was thinking that, there's the primitive ninth root of unity. But now if we're working over the Gaussian field, then that primitive ninth I was thinking, like, what happens to that primitive ninth root of unity over the Gaussian field? Does it like factor into something else? But I'm not sure that's a sensible question, because it's not like it was a prime that could suddenly factor. I mean, it was an invertible element, the primitive ninth root of unity under multiplication. So, so I don't know. I'm getting a little bit close to the point here where I should quit and let you start talking. But let me try to. Let me just try to give a little bit of motivation for some of what I'm trying to do here, okay? So maybe I should go to a new page here. Let's see. Well, in a moment, I'll probably go to a new page. Or actually, right, I don't actually need pages here. I can just scroll down. Sorry. Am I doing this? I'm having trouble figuring out how to scroll here. Oh, there it is. Okay. So let's think about the Torser viewpoint for a moment. And you're not happy about the idea of just shifting back and forth between the Torser viewpoint and the abelian extension viewpoint. But nevertheless, let's think about the Torser viewpoint here for a moment. So one of the things about the Torser viewpoint is if you have two Z mod 3 torsors over a given number field, then you can tensor them together and get another Z mod 3 torsor. And like, so for example, like if you have one Z mod 3 torsor that corresponds to the cube roots of a given number A and another one that corresponds to the cube roots of a given number B, then the rough idea is that the product will correspond to the cube roots of A times B. And so if A is prime or close to prime, and if B is close to prime, then A times B will be not so close to prime. So what I'm saying is that the ones that correspond to prime, the torsors that correspond to the prime numbers, I'm being very sloppy here, but roughly speaking, the torsors that in some sense correspond to primes here are giving us like a special basis of this cohomology group. Whose elements are the torsors. And so that means when we're trying to classify these torsors, we can try to take advantage of this fact that there seems to be a sort of almost canonical basis for the for this cohomology group of torsors, and not just a canonical basis, but a seemingly rather nice canonical basis, because of the way it's associated to the primes or something like the primes. But one of the flies, one of the many flies in the ointment here. Ointment is full of fly. One of the flies in the ointment here is that I'm not sure exactly how canonical this basis is, because there is like there's just a little bit of ambiguity in it, and it seems to be caused by this Well, like for example, let me go back to, instead of Z mod 3 torsors, let me go back to Z mod 2 torsors.
Mm-hmm.
So there's a Z mod 2 torsor for the square roots of 7, and there's another Z mod 2 torsor for the square roots of -7. And, you know, because 7 is prime, those are both good candidates for what should count as a prime torsor, you know, a torsor in the special basis. But it's just very hard to decide, for me at this point, it's very hard to decide which one of those two would be, you know, would be more canonically, because I'm right, because they differ by a factor of -1, and -1 is this sort of quasi Conway prime. It's not a real prime, but
Those,
I guess those Conway primes seem to be, at this point, I'm blaming Conway for this, that they seem to be these flies in the ointment that don't act like regular primes or something.
is there a torsor for -1 just by itself?
Let me think about what you're saying. I think, yeah, so that, yes, and that's the one, that's this very super special one,
Uh-huh.
is the Gaussian field itself, as an extension of the rationals, because that's the square roots of -1.
Mm-hmm.
And right, and right in the world of Z mod 2 torsors, that's the analog of this thing that we're dealing with in the world of Z mod 3 torsors, where it's the primitive 9th roots of unity, right? For 2, it's like the 4th roots of unity, you know, like I and -I and stuff like that, the primitive ones. Whereas when you're dealing with the Z mod 3 torsors, it's these primitive 9th roots of unity that are sort of making it difficult for me to figure out exactly what the real canonical basis should be. Because, you know, like I say, you know, if you have like, if you have one of these numbers whose cube roots give you a torsor, then you can just multiply that by any, instead of taking the cube roots of x, you could take the cube roots of x times a primitive 3rd root of unity. And that will be another torsor. And it's hard to tell which of those 2 torsors, or there's actually 3, a little triplet of 3 torsors there. And it's hard to tell which one is the most important, which one deserves to be the basis one there, or something like that. So very roughly speaking, you know, it's very roughly speaking, it looks like there wants to be a nice basis corresponding to the primes, but the Conway primes are introducing this extra confusion. I mean, that's a very sloppy way of describing it, but that's what the situation is. And so all of this stuff that I'm doing here with this, I'm gesturing here with my cursor here back to the tablet. All the stuff that I'm doing here, trying to analyze the subgroups of this Galois group, is related to that, because do you see what I'm saying? It's like the flies are even worse than I thought. I mean, not only do we have the primitive 9th roots of unity acting as a fly in the ointment, there's this extra imaginary fly, and it's like some weird cousin of the imaginary cousin of the 9th roots of unity. I don't know. I can't figure it out. I mean, you know, I'm really understanding things better now, but I see that, you know, I have to understand these better. This is, you know, so this is real homework for me to clarify this. But I'm hoping you can see I'm hoping you can get some idea of the gritty calculations, but also the conceptual issues behind the gritty calculations. And I'm hoping we have enough time for you to talk now. So is that going to work?
Yep. Yeah, I know I would have infinitely many questions about this.
All right. Do you want to ask any of the infinite questions right now?
I said I had infinitely many, not one. So
Well,
okay,
I don't have to give all of them right now, but
yeah, okay, I have.
but okay, that's a good reasonable excuse for not
Sometimes
asking.
you need the axiom of choice.
If you have too many, so
infinitely many things to choose from.
Having too many is, I guess, an excuse for not asking.
Well, I'll ask one. Like,
okay.
How generally do you suspect that this norm equals one condition?
Yeah.
Like the right way. So that's, in this case, you're saying that's the way to tell which primes split?
I think so. I mean, there are so many calculations here that I need to check.
Okay. So maybe premature.
So many guesses. I call them calculations sometimes, but a lot of them are guesses.
Right. So anyway, one of the things you may be curious about is like, how general is that as a condition for when primes split? Like not just in this case, but like in other similar cases.
Right. And I think that's a general rule. I mean, we talked about that like 2 weeks ago or something like that. But we really need to clarify that further. But so that's right. That the application of that general principle that you're hinting at there, the context where that general principle should apply is like, whenever you're algebraically pushing forward or geometrically pulling back an extension along another extension. Or perhaps, specifically an abelian extension along another extension, or maybe an abelian extension along another abelian extension. We're not sure how generally you can apply it, but
yeah, I would love to know these rules sometime.
Right. Certainly one place, right. One place where it should apply is when you're algebraically pushing forward one abelian extension along another abelian extension, and the resulting push forward is itself still a field, rather than one of these things that breaks up into multiple fields. So in that situation, this norm rule should make sense and should be correct, but we need to check whether that agrees with what textbooks say, and check whether it's true, and et cetera, et cetera, et cetera. So yeah, that was my attempt to answer your one question.
Yep.
So you're done with the questions for now?
Yep.
All right. So maybe we can just stop the recording for a moment while I regroup here, and then you're going to talk for a while.
Sounds good. Let me pause this thing. Okay. Yeah, so I've been thinking a lot about separable algebras and getting really excited about the big picture, and there are lots of smaller details that need to get worked out to fill things in, which I've been doing. So so what are the deals? So there's like a classical situation, which I'm sort of trying to understand and also generalize. And so the classical case, I'll call it, which I will always use as an example to motivate me, is you've got like a field, and then you get this symmetric monoidal bicategory of, okay, now I want to stop my video because it's getting annoying.
Okay.
Okay. All right. So slow, I can't even stop my video. Okay.
All right.
So you get this symmetric monoidal category that I keep on talking about. which are like algebras over that field. And then bimodules. And then bimodule homomorphisms. So but this is sort of like the playground in which I want to think about various things.
Sorry, I'm just catching up because I was,
Yeah.
trying to write stuff down. So algebra here means associative algebras?
Yeah.
No more, no less. I mean, roughly speaking. Yes, okay.
Unital associative. Yeah. Uh-huh.
Okay.
Because
Associative algebra is exactly what to ask for, what to require.
yeah, that's what I'm trying to do. So
Okay. And by my yes, and not only right, and this makes sense, right? I see why this makes sense. This seems like the sensible thing to do, right? Okay.
Okay.
I mean, you did mention how that within here you can focus on commutative things. Boy, that
Right.
and that
I
really
am going to focus on commutative things sometimes, but then sometimes I'm not, and I'm trying to understand how they all.
Yeah, I mean, I know you've been talking about this already, but I'm suddenly realizing how sensible and interesting a thing that it is to do that, and to place it in this larger context. So go ahead. Yeah.
Right. So just sort of like for formal purposes, I will note that this is what's has actually been worked out as a compact closed or compact closed bicategory, meaning by which I will always mean a compact closed symmetric monoidal bicategory. So every algebra has this other algebra, it's opposite algebra, which acts as a dual object in the sense of monoidal bicategories, which is a lot like the sense of dual in a monoidal category, but suitably weakened. I could sink into technicalities about that because it's actually, the theory of duals and monoidal bicategories is sort of interesting. You probably can, but I don't really want to sink into the details now. It's just that.
Yeah, no, that's okay.
Yeah. So, but it's just that the only reason I'm mentioning that is that that sort of serves as a kind of basis of what I might call like the general case. So I'm trying to generalize classical stuff while also just trying to understand the classical stuff. So the general case would be just, I've got a compact closed bicategory and I'm going to do stuff that I can do in there. So the reason why I'm interested in that generalization, the original reason why I'm interested in that generalization is that I was very interested in the case of super algebras and so on. So so for example, in the case of where K was the real numbers, the super algebras over it form a very interesting compact closed bicategory that lets you generalize the Brouwer group of the real numbers to this 8-element super Brouwer group. And all of that fits, and all this stuff about the tenfold way fits into this framework, or at least a lot of it fits into this framework when you do that super case. But I decided I wanted to be more general and just see if a bunch of this stuff that shows up emerges for any compact closed bicategory. So that's sort of like where I'm going. Okay, but the reason why it's interesting is that there's a lot of cool stuff that happens in the classical case that seems like it can be generalized. And in particular, I seem to be getting several sources of inspiration for ideas to work with this symmetric monoidal bicategory, which overlap in a way that's sort of intriguing and confusing to me.
Yeah.
So one sort of one really interesting thing, I guess I'll just like call it Brouwer theory, or following your tendency to elaborate things. Maybe I would call like, I won't keep calling it this, but it could be like called like Azumaya Brouwer Picard theory.
Uh-huh.
Not listed in any particular order, but the idea is, as I've explained before, and you can take the core
Yes. Yes.
of this compact bicategory.
Yes. Yes. Yes.
And then you get a 3 group.
I get it. It's hopeless to try to straighten this out, but is it? So why did Picard has a C in it, but does not actually start with C? Is this 012, or is it 210?
The numbers here?
Yeah.
Not
I mean,
any particular.
it depends on which way you think of it, probably, but yeah.
Well, not really. Not really. No, I mean, those are just the 3 folks. So as a 3 group, you have like
Or 1, 2. Okay, you're using 1, 2, 3. Yeah.
I don't know. Maybe I will call it 1, 2, and 3 because yeah, you have that choice of numbering scheme as well. But at least everyone knows that pi 1 is a group. So let's this is sort of like that. So pi 1 is, if we do it in that numbering scheme, then pi 1 is the Brouwer group, and it contains representatives of these invertible algebras, which are called Azumaya algebras.
But you've really got some weird permutation of 1, 2, 3 here. Is that right?
Yeah, no, it's just like it's in alphabetical order. It's not even a permutation of 1, 2, 3. It's just because Brouwer and Azumaya both belong in pi 1. Yeah. So pi 2 is the Picard group. So it's the group of invertible.
Oh, I was hoping we could actually get the AB thing to work out somehow, but
yeah, no, not in particular. And then pi 3 is called the units groups. So that's not a person's name, unfortunately.
But there's nobody we can blame for that? Let's see.
Yeah, I don't know who invented the idea of the unit group of units of a field or of a field or of a commutative ring. By the way, going back to this classical case, so this classical case is like the extremely classical case is when K is a field. And then there's also a huge amount of work on the case where K is a commutative ring. All this makes sense in that context, and that's really important source of inspiration.
So I'm not even sure to what extent I've ever rigorously read about compact closed bicategories. I mean, maybe I have and just forgot or something like that. But
my student Mike Stay wrote a paper called "Compact Bicategories" or "Compact Closed Bicategories." That was sort of so I went through a bunch of that stuff at some point.
Okay. But it looks like there's a really good chance here that I mean, you may have mentioned various technicalities that you don't want to talk about, but I think there probably isn't any technicality. Is that right, about whether the algebras are finitely generated or anything like that?
I'm putting them all in here. Then when you get to the invertible ones, then they turn out they need to be finite.
Well, but you can just say take the invertible one.
Right. Yeah. So I'm saying when you take the invertible ones, you go to here.
Yeah.
Then there are various properties, the various characterizations of Azumaya algebras, and part of what I'm trying to do is to understand those characterizations.
Yeah.
In the general context, but in the special, but This guy, Niles Johnson, wrote a wonderful paper about this type of stuff. But
Okay.
anyway, so in the classical context, or like even in the semi-classical context where this is a commutative ring, the invertible algebras need to be finitely generated and projective. Yeah, so.
But again, when you say need to, it's not like you need to put that in. It just automatically.
Yeah, no. I mean, no, they are, yeah. To be invertible, it's a necessary but not sufficient condition that you're a finitely generated projective.
Right. I was just hoping that, that there wasn't something that you had to put in by hand here, and there
No,
is.
no. Yeah, there isn't. So it's very nice. Yeah.
Okay.
Yeah, so it's very nice that way. But I'm just saying that, like, all those extra consequences of invertibility.
Right. I mean, again, I need to check all these details later, but that's good enough for now.
So yeah, well, that's a long and interesting story. That is what
Sure.
what follows from knowing that something is invertible. And that's the kind of thing I've been studying.
Sure.
So anyway, there's this source of inspiration, and I'll just say, like, further inspiration for me is the fact that in the classical case, so that is algebras over a field, it turns out that these invertible algebras, these Azumaya algebras, are exactly the same thing as central separable algebras. And I finally really understand the proof of that, which is very beautiful, sort of. And so, just for the audience or something, so central means that the center of it of the algebra is just the field, and separable, there are many equivalent ways to define it, and that's part of the fun there too, is to, like, why are all these ways of thinking about separability equivalent? But there's one way that's sort of very easy to define there's one way that lends itself to being generalized to the general case. And it's just, and I mentioned it before, it has a nice string diagram description, which is the sort of thing that you can use in any compact bicategory. Let me call this algebra A here, I guess. So what I just want to be able to talk about it. So here,
by the way, sorry. Just if I do want to put these things in order, then the correct order is Azumaya Picard units. Is that right?
Yeah.
Okay. Sorry for the interruption. Sorry.
Yeah.
Go ahead.
Yeah. And the group of Azumaya algebras is called the Brouwer group. So he's sort of also down there.
Okay. Oh, okay.
That's why.
Okay. So it shouldn't be Azumaya. It should be Brouwer. Okay.
Yeah, if you're going to call them groups, then yeah.
Right. So the Azumaya things are the elements of the Brouwer group, roughly speaking.
Yeah. Lots of fancy names. Yeah.
Okay.
So in the classical case, the Azumaya algebras turn out to be exactly the same as the central separable algebras, and the separable.
Wait, that's funny that the units has units and units. The elements are called units, and the group is called the units. That's annoying. Sorry. Go ahead.
So the elements? What elements?
Of the units group.
Oh, the units group. Yeah, right.
I mean, Picard has the elements called lines.
Right.
Brouwer has elements called Azumaya.
Yeah, no, there should be somebody's name who we can blame for discovering that.
We need two people. Well, line is
at least one.
Okay.
So, okay.
Oh no,
so,
actually, wait a minute, it is. No, wait a minute, there is something here, right?
What?
Well, with the Brouwer thing, we also dignify the elements with the person's name. With Picard, it's only the thing itself gets dignified with a person's name. And with units, we don't even dignify anything with a name.
That's probably how it goes, yeah.
And
But I mean, for some reason, as you go
that's
high,
the really important discovery. Go ahead, yes?
I mean, for some reason, as you go higher up into these pi ends, you go lower down into like they get to be like simpler things to discover. So that everybody knows what a unit is. Only Picard, yeah. So as you go down here, it gets like more elevated sounding, yeah.
Right, okay.
For some reason. Some real reason. Okay, sort of into it. Okay, so central separable algebras are these Azumaya algebras, and they are ones that have this co-multiplication, a kind of co-multiplication. It's not so something going from A to A tensor A, but it's not a we're not demanding ahead of time that it's an algebra co-multiplication. What we really want is that this
That it's a co-algebra co-multiplication? That it's an algebra co-multiplication? Oh.
we're not demanding primarily that it's a co-algebra.
That it's a co-homomorphic, that it's a homomorphic, right? The co-product is not a priori a homomorphism of algebra. Is that what you're saying?
No, well,
Then what are you saying?
that's true. I'm just saying that I'm not even demanding that this is an algebra homomorphism or a co-algebra. I'm demanding let me tell you what I am demanding. Okay, that'll be faster.
Okay.
It means that I'm not saying so. What it is it's a bimodule homomorphism, an AA bimodule homomorphism.
Right.
So it's an AA bimodule map that splits the map that's multiplication.
Sorry, just a pretty stupid question here. So it just the stuff you're saying reminds me of stuff you've been saying, not just today, but stuff you've been saying reminds me of stuff in this book by Joachim Koch. Is that's a non-coincidence? There's some
That's a non-coincidence. Yeah, the stuff about 2D TQFTs is also showing up here. Yeah, it's taking me a long time to.
Are you saying that that's what that book is about? Two-dimensional TQFT?
Well, that's the book that I thought you're talking about.
Okay,
yeah.
well, I just think of it as, a book. But you may be right that it's a book about two-dimensional TQFTs. Okay.
So this is what it means to be separable. I guess splitting is ambiguous if I don't say like which one is the section and which is the retraction.
So, sorry, is separable defined in a way? Separable is only defined once you have central, or separable?
No, I'm defining that's crucial, that I'm defining separable. Central is this, separable is this, and we're going to be interested in other kinds of separable algebras too.
That aren't central.
To the grand scheme of things.
Okay. So, okay. Algebras that aren't central. All right, I'll have to think about that.
For example, the commutative separable algebras are going to be super interesting. So like a field extension of our field if it's a separable extension, it'll be a commutative separable algebra over our field that will not be central because its center is bigger. So part of what I'm aiming at here slowly is I'm talking here
about. Wait. Say that again. I didn't follow that all. Can you say that again? What? If you have a commutative what? If you really don't want to say it, but yeah, go ahead.
You're getting me into part 2 here, but let me not talk about it now. But there are tons of really interesting separable algebras that aren't central, and that's part of the whole point of this.
Okay.
What I wanted to do is just draw a picture of what it means to be separable. So to be separable, it means that you have. I did this once before, but I'll do it again. You have this co-multiplication, which is a kind of in string diagrams, one thing splits into two. And the fact that it's a section says that if you co-multiply and then multiply, that it's the identity. And then the fact that it's a bimodule homomorphism means that it obeys two other equations that say that you can act on the left and after or before you do this co-multiplication, or you can act on the right before or after and you get equality. So these are usually called the Frobenius axioms, as you know. And this thing, sometimes it's called the separable axiom, but I prefer to call it the special axiom, special Frobenius. But my point here is that these are the sort of things that you can, because they're string diagrammatic, they're very easily generalized to the general case. They're very there's sort of things you can talk about in a monoidal category, and so somehow that lends themselves to be talked about in this bi category. Although it's not. Yeah, I'll just leave it at that. So it's very primitive mathematics in a sense, not a lot of existential quantifiers and stuff. Although the separable just actually does have a quantifier in it. It actually just says that there exists such a splitting. We are not actually acquiring it as a property. We could do that, and that will change the sort of flavor of the subject a bit.
Right. Okay. I'm just trying to catch up a little bit here. So you're saying that you have this thing that you're notating as a triangle. Do you call that a delta, a triangle?
Yeah, delta. That's like the usual notation for a co-multiplication because it looks like one thing's splitting into two.
Oh, I thought it was because delta stands for diagonal.
Oh, that's true, and it stands for duplication as well. Yeah, so it's great. Yeah. Yeah, probably diagonal was the original origin of it.
But now you got me wondering about all those other words we were notating with D, like division and distance, and I'll have to think about that, whether that cluster of D is related to this cluster of deltas. So okay, delta, and again, there's this issue which I'm willing to not stare too closely at, about whether we're thinking of this as a property or a structure, but you are saying that this thing is special and Frobenius.
Yeah, that exhausts the content of this verbiage here, that it's an AA bimodule map. So that's the Frobenius.
So that special and Frobenius is just a paraphrase of.
Yeah, I was just saying that I'm taking this junk and I'm pointing out that you can write it down using string diagrams, and that means that that lends itself to generalization to other compact bi categories, because when you're working in like compact n category, the string diagrams are what you kind of way you can assert statements. It's a sort of primitive kind of logic.
Okay.
Yeah. So there's this whole subject.
Yeah.
And so it lends itself to all sorts of fun things. Like you could take a field and you could try to calculate its Brouwer group.
Yeah.
And so on.
Yeah.
And so and so on. So that's interesting. Okay, but then there's this other source of inspiration for studying this compact bicategory, which overlaps in a really interesting way. And I guess this other angle on things, people seem to call it like Grothendieck-Galois theory. Grothendieck-Galois theory. I don't know quite why they call it that. Well, except that Grothendieck did make a lot of advances in it. So here, what are we doing? So here, instead of looking at the central separable algebras, we're doing something quite different. We're looking at the commutative separable algebras. Looking at the commutative separable algebras. And that's supposed to make sense in the classical case, but I just want to emphasize that these can be defined perfectly well in the general case too. Although maybe you would say monoids, and maybe algebras would not be the word for what they are, but the point is that well, I don't want to get into it too much, but using the bicategory stuff, you can define this concept in the general case. And so it's just as general as the first realm of investigation. But what's nice about, or what's intriguing about this, is that in the classical case, we get this result, which is the commutative. If you look at all the commutative separable algebras, take the category of them and algebra homomorphisms. So notice algebra homomorphisms, preserving the multiplication, not preserving this other co-multiplication, which is, I'm just thinking of it as an existential property then. So, and then we take the opposite of it, we get a topos, and it's a very nice topos. It's okay to be sort of pedantic. It's equivalent to the category of what? Finite. No, let me just make it look really slick here. So continuous actions of the Galois group, the absolute Galois group of K, on finite sets. So maybe that's like a dumb way to phrase it, but so finite sets that have a continuous action of this Galois group. And this continuous baloney is referring to the fact that this is like a technical trick that you're familiar with. Probably,
Sure.
I think Gal K is a profinite group, and it gets a topology, and then its continuous actions on the finite sets are those factor through a finite quotient of that Galois group.
Not to be too digressive, but have we ever talked about the issue, I should say the question of, are profinite groups, are those the same thing as, I want to say sort of like Boolean algebraic groups?
I think that's quite, I think that could be true. Yeah, I think there's I think I was just reading something relating profinite groups to stone
Yeah.
space. Like they're like stone space groups.
Right. That might be
Sort of what you're,
okay. Again, we don't have to worry about this right now, but I think what you're just saying is sort of like along the lines of what I was suggesting. Yeah, something like
yeah,
that.
yeah. And that's really nice too, of course, as you know, because there's this nice way that, well, you just sort of said it. There's this nice way that stone spaces show up in logic due to the fact that the category of stone spaces is the opposite of the category of Boolean algebras. So, yeah, so, right.
Okay.
So I'm just sort of, so just mildly hinting at all that realm of investigation that this people will go around saying that this category here is a Boolean topos. Boolean topos. So, I mean, there's this logic side of stuff that's beginning to show up here.
Yes.
But also, of course, there's just the Galois group of your, I mean, if you were not care about logic and you just think you're studying algebra, then you'd get interested in this just as a way to think about the Galois group of
Yes.
your field.
Yes.
And so there's some very intriguing to me interaction between this part one, where we focus on central separable algebras, and this part two, where we focus on the commutative separable algebras, because, for example, well, I mean, for example, I mean, obviously, it suggested you should at least think a bit about all separable algebras. So if you take any separable algebra, then it will have some center, and it will, that center may not be your original field K, but its center will be some commutative separable algebra, actually. So the center of a separable algebra is a commutative separable algebra. So it's sort of like, so I like have this kind of picture in my mind. It's a very vague picture. So like we've got like our field K, and then we've got these central separable algebras sitting over it. They're bigger than it. But if you'd like try to get an algebra that's too big, so here's K down at the bottom. Here, like we go up and we get a bunch of central separable algebras. And so like these guys here are like forming the Brouwer group. I mean, they're equivalence classes of them forming the Brouwer group. But then like if you go too far, you might get an algebra whose center is actually bigger than K. So you're like above the level that the Brouwer group can see. So like the Brouwer group of the real numbers doesn't see the complex numbers, for example. It's like too far up. But
say it again, the Brouwer group of the real numbers doesn't see the complex numbers. Is that what you said?
Yeah, so like the Brouwer group of the real numbers just has two elements, which are like the real numbers and the quaternions. Those are that's the Z mod 2 in the tenfold way.
All right,
Sorry,
okay, yeah.
sorry. Forget the tenfold way. No, that's the super stuff. The Brouwer group of the real numbers is just real numbers in the quaternions. But there's another important separable algebra over the reals, which is the complex numbers, and it's not central. That's why it's not seen in the Brouwer group. It has a bigger center, and that particular one's a field itself, of course.
Oh, okay. So maybe I didn't understand what you meant by maybe I have not been understanding what central means all this time. So essentially like a snugness condition. What?
Yeah, well, you said when I said something like you could take a field extension of your field, and if that's a separable extension, that would be a separable algebra over your field. But it would never be central because its center is bigger.
Let me just write down a quick note about this so I can pay attention to the rest of what you're saying. Brouwer group of R doesn't see. C isn't central.
Yeah, this is exactly what I'm interested in. So that is, let me just remind you, like when I was talking about the tenfold way, I had this, the tenfold way had this 8 thing and this 2 thing, right?
Yes, right, yes.
So like the 8 thing was, turns out that was like the central separable super algebras over the reals. And the complex numbers are not in that 8. The complex numbers are I'm sorry, there's so many adjectives. It's a super algebra that's separable over the reals, but it's not central because its center is bigger. And so
but
then you get its Brouwer group of the super Brouwer group of the complex numbers, which has 2 elements. So I was drawing this picture here where I'm trying to like explain like the type of thing that happens is that you get like a bunch of central separable algebras over a field, but then as soon as you go to a field extension, it's like, I just vaguely imagining this like too big in the sense that its center is bigger. And then it will have its own central separable algebras over it.
So can I, again, I'm always searching for excuses here. Is it possible that there is somebody somewhere who uses the word central in a conflicting way to the way that you're talking about? Because I think I've often imagined that when people say central, they usually just mean, right? there are certain old-fashioned people who didn't insist that algebras be weakly central. And so, sometimes I thought central was just saying that,
I don't, there could exist such people. We could probably dig them up out of the graves of.
But you think almost that all the time when people say central.
When people are talking about like central algebras, yeah, I mean, and in this subject of Brouwer theory or something, yeah, they always.
So the emphasis is the emphasis on the meaning of central is that
yeah, I see.
It's not that is not that the thing is small enough to be in the center, but that it's big enough to be the whole center.
The field is big enough to be the whole center of the algebra, yeah.
Whereas I was imagining, that there was, in the old days, when they were saying central, some people were just emphasizing that the field isn't too large to be in the center.
Yeah, no, I mean, I don't want to think about.
Yeah, no, but
algebra.
I just need to orient myself to this terminology because I
Sure.
honestly wasn't particularly familiar with
Okay, well, that explains.
ubiquity of this centralness terminology.
Okay, well, that explains some of this somewhat strange things you've been saying. Now I understand why you were
Okay.
acting that way.
Okay.
So yeah, so it's an incredibly important point. So like here I'm drawing like in some very vague way algebras over my field K that are still small enough that the center of them is just K and no more. But then if we go too big in some sort of sloppy sense, we get algebras whose center is bigger than the original field. And their center doesn't need to be a field anymore. It could be
Yes.
it could be any commutative separable algebra. But which will be like a sum of, or sorry, product.
Yes.
A product of fields. But it's especially interesting when it's just a new field that's a bigger field extension of your field.
Yes.
And then, but regardless of whether of that or not, that new bigger commutative separable algebra, you could take that as a new base, and you can look at its Brouwer group. So it's especially classical when it's a field, but you can look at its Brouwer group defined in the exact same way that I've been defining it.
Yes.
And so you like explore more, or I don't know, you explore like a higher level, not more, but like a higher level of the whole big mess of the whole big poset or some whatever category of separable algebras.
Yes.
Yeah. So I'm really interested in that because I think that hasn't been discussed quite enough, and it's sort of the thing you got to think about when you're trying to connect this Grothendieck-Galois theory, where you're like completely focused on the commutative separable algebras, and you wind up sort of thinking of them as giving you like covering spaces of some space, and you can like keep on going up and up and up to higher covers.
Yes.
So that's very visual.
Yes.
And then this Brouwer theory,
Yes.
where you're dealing with non-commutative algebras, and they have a different flavor to them. So it's sort of like they're non-commutative covers of your original space. But I don't want to just like say that and be terribly sloppy about it. But I mean, so what they really are, in the classical case or semi-classical cases, these Azumaya algebras. But part of what's really interesting about these Azumaya algebras is that they do have a kind of geometrical interpretation. You can think of them as basically, now I'm getting sort of hand wavy, but it can be made precise, that you can think of them as like bundles of matrix algebras over your space.
Yeah, you mentioned that previously. Yes.
Yeah. That's connected to the fact that this Brouwer group is a cohomology.
Yes, that's right. Yeah.
And so,
I mean, that certainly sounds like it makes sense. Go ahead. Yes.
Yeah. So that's. So
I mean, there's subtleties there, but yes, go ahead. Yes.
So I sort of want to.
I mean, can you just say what kind of subtlety I was imagining there? I was imagining that. I was wondering if you're getting up to the level yet where the local trivialness has a Zerby feeling to it yet.
Yeah, it does. Yes, it does. Yeah. So
Okay, well, that's good enough. Okay, go ahead. Yes.
yeah, that's right. Well, you can think of them as bundles of algebras, but you
Yeah.
can think of them as gerbs whose structure group or band is the is the what do you call it, like the multiplicative, it's the multiplicative group, or you would sort of like say like the O star of your of your of your
Yeah.
of your scheme or what. Yeah.
Yeah.
So,
Yeah.
so you can think of, yeah, so you can think of, so
I mean,
the
it's the
idea
next
is,
game past the Picard.
right. So you can, so the Brauer group is, I mean, there are more and more subtleties that I don't want to get into, but roughly
Sure.
the Brauer group is the next thing after the Picard. It's H2 with coefficients,
Yeah. Yeah.
multiplicative group thing, just the way,
Yeah.
in the same sense that the Picard group is the H1.
Yeah.
But the thing is, you can twist a trivial bundle of matrix algebras by a gerb, and you get this sort of non-trivial bundle of matrix algebras. So all of that's really interesting, and it's
Again, sounds plausible. Yes, go ahead. Yes.
all of that's really interesting in itself and worth thinking about. But what I haven't seen people talk about enough is like, what's the right way to think about all that stuff in conjunction with this Grothendieck Galois theory approach, where you're thinking of.
Yes.
So I sort of have this. So the picture I'm sort of having here is, take a look at this thing, Jim, just for a second. It's just like this vague. So the idea is like you've got a space. I mean, now I'm thinking of K as like some space.
Yes.
And then it's got on the one hand, it's got covering spaces, which are again like actual spaces.
Yes.
But then on the space, they're like all these gerbs, or all these bundles of matrix algebras.
Yes.
Which are sort of they're not as like far, they're not real covers. They're not as far up as as an actual covering space, but they're still sort of above the space in some sense.
Yeah.
Like bundles of matrix algebras over that space. But they all sort of fit into this, big picture, and you can take any one of these dots here, which is, all these dots are supposed to be the central, all these dots are supposed to be the separable algebras over K. You can take any one of those dots. No, you can take any one of the ones that's commutative, and then you can work over that as a new base. Yeah.
Yes.
Yeah. So I'm trying to understand that better. It's basically.
Yes. Yes.
So
Yes.
that's basically enough of the spiel. I'll just say like a couple of things that like
Yes. Yes.
play into this in some kind of like more mystical
Sure.
things. So there's this thing that you were alluding to, which is that like commutative Frobenius algebras give TQ 2D TQFTs. There's actually some kind of equivalence of categories of those.
Yes.
And then there's this other thing that special Frobenius algebras, that not necessarily commutative, but special Frobenius algebras. There's a way to use to get some kind of QFTs from them. They're called I don't know, 2D lattice TQFTs.
All right. I mean, this sounds interesting. I might have to. It sounds like interesting in the sense that there might be a lot of stuff I might need to learn here. Again, might I be able to learn any of this stuff from that Koch book?
You can learn everything about this 3 from the Koch book. Yeah.
I was actually asking about 4 though, whether the 4 is
I think nothing. I doubt he talks about
okay.
it all.
Okay.
I'll just say about this 4 business. This 4 business is like where you take a 2 manifold and you chop it up into triangles.
Right.
And then you think of this triangle as like, you can think of it as like a multiplication, because you can think of it as a map from 2 things down to 1. But you can also think of a triangle, and this is really the origin of the delta here, right? you can also think of a triangle as going from 1 thing to 2. And that's where this that's where that delta or co-multiplication thing shows up. And then all these string diagram rules that I would have been listing before.
I hadn't really appreciated that the level of seriousness that you can really get into about this delta thing and the sort of Poincare duality between the delta shape, but the shape of the river that's forming the delta. You know, exactly. You really have that string diagram. The river is this, the branching river is the string diagram.
Yeah, I guess rivers don't really, I guess they branch in the
but
they branch if you're swimming upstream, yeah. I mean, saying the river branches that's I guess what
I don't know, but I was talking about a delta. I
am drawing a delta. It is right. This is the shore here. These are the rivers coming in. Shore? Oh no, never mind. Yeah, forget it. That's
all right. Things are getting complicated here, but still, I should
go. That's
not
what a delta actually looks like. You're right. A delta does branch when you get near the shore, but that's.
I'll have to think about it. You know, maybe this is all going to work out, or maybe it's going to come.
It looks like it's not working out at all to me right now.
I'll have to think about it. Go ahead. That was in. I interrupted. Go ahead. Back to where you were. Yes, you're looking at manifolds, triangulated surfaces. Yeah.
So some people working on 2-dimensional field theory get really interested in special Frobenius algebras.
Say that again. Some people who are working on TQFTs get, or these are non-T. Does it really deserve?
Yeah, they are TQFTs, but they.
I mean, it's funny having the letter T in there with the word lattice, but I guess there's something going on there. Yeah, I mean, this is a standard thing.
But the point is that you use all the axioms to show that that a bunch of stuff doesn't change if you change the triangulation. So you use these axioms for special Frobenius algebras can be motivated from axioms about like Pachner moves and such, changing triangulation. So yeah. So anyway, there's that, and then like one last thing to throw in. There's this idea that has been running around that picking a basis for a vector space, for like a finite dimensional vector space, is the same as making it into a commutative Frobenius algebra.
Sure.
So so that idea is running around in the literature on foundation of quantum mechanics these days.
Yes.
Where they would typically work with Hilbert spaces, but
yes.
but that idea that like, so the way they say it is like, if you want to like relate, this is sort of a, I don't like this way of saying things exactly, but the idea is that like, if you want to understand how sets with their classical character are lurking in the category of vector spaces with its quantum character,
Yes.
you think about, you should think about free vector spaces on sets. So you should think about sets with a vector spaces with a basis. But if you think about how that basis manifests itself in the category of vector spaces, it's making the vector space into a Frobenius algebra. And I guess it's actually making itself into a commutative special Frobenius algebra. So people in the quantum community have been talking about things that way, but they don't seem to have read Aurelio Carboni's paper on this subject. So Carboni and Walters, and then later Carboni, have been talking a lot about special Frobenius algebras as a structure that shows up when you are trying to relate their compact category to a Cartesian category. For them, the fundamental example would be like the category of sets and the category of relations. There's a functor from sets to relations, and then any set, I guess any set gives you a.
I mean, this is reminding me of Cartesian bicategories or something?
Yeah. That's what I'm talking about. There's stuff on Cartesian bicategories. Yeah. So these are different ways that this separable algebra.
Sorry, just another stupid question. Have you talked to Todd much about that?
I have a bit, and he's been sort of busy, but he wants to say more about it. He got interested in this paper by Aurelio Carboni.
I mean, it's just that Todd is really interested in Cartesian bicategories.
Right, yeah. So he knows that Cartesian bicategory stuff really well. And then there's like some stuff in his Carboni paper that goes a bit further than, or different, that he doesn't know about. And he wants to read about it, but he's been too busy. Yeah, I'm going to try to rope him into aspects of this.
Okay.
So all these items 3, 4, and 5 are sort of like propaganda for how some kind of sense in which like item 1, the Brouwer stuff, is sort of in the sense that it's dealing with non-commutative algebras. And then 2 is sort of classical, well, not in the sense of just as opposed to quantum, but very non-classical in the sense of, well, I guess of the Boolean topos, but anyway, more like classical logic. And so they like somehow interact with each other in some interesting way. Yeah. So, and I want to understand that a lot better than, and I want to understand it all as much as possible in the level of like, someone just hands you a compact closed by category and you work within there.
Just another silly comment is that as you're discussing these ideas, I still want to try to relate these ideas to humble ideas about functions versus matrices as a basis for the relationship between classical versus stuff.
Yeah, that sounds good.
Functions as diagonal matrices. What? Yeah, go ahead.
Yeah, I may have told you already, but I'll tell you again that Aurelio Carboni's paper has a superficially humble title. You may have even stolen the phrase humble from me there, because his title is something like
Right, you did tell me that. I forget the title already, but it was, what was it?
Matrices, relations, and something else.
Uh-huh. Mhm.
Something else equally humble sounding.
Yes, yes.
And so then it may come as a shock to the naive reader to discover that it's about Cartesian bicategories. But that's definitely, yeah, that's sort of along the lines I think that you're trying to.
Yeah, I'll have to think about that. I'll have to think about that, but it sounds very plausible. I'll have to think about it.
Yeah, anyway, he
Okay.
sounded like he was trying to say, like, this stuff is really fundamental.
Okay.
Let's see. Yeah, one other thing I'll say.
Yeah.
Yeah, I sort of said this already, but Carboni defines central separable. Sorry, not central. He doesn't care about central. He'll define separable commutative monoids in any symmetric monoidal category,
Yes.
because you can do it using these string diagrams.
Yes.
And then so he looks at the category of commutative separable monoids in a symmetric monoidal category, and he'll take its opposite, and he doesn't quite get that it's a topos, but he gets it's a Boolean pre-topos.
Uh-huh.
So he's trying to, like,
Yes.
get this going at a high level of generality. So that makes me want to do
Yes.
that too. Yeah. There's a lot of other stuff to say about what he's doing that's like less
Uh-huh.
flashy sounding than that, but just very nice one.
Yes.
Yeah. So anyway, it's all this stuff is really exciting me, and also like really bugging me because there are lots and lots of questions that show up. But
Yeah. Yeah.
I am actually making some progress in it.
Uh-huh. Uh-huh.
So I don't know if you have anything to say about this general mess, or if you've
What? Say it again. About what?
general mess, this general bunch of stuff.
I really, there's so much here that I haven't thought about at all deeply that I really need to think about more before I can.
Uh-huh. Okay, well, I'll keep talking about it until you do think about something.
Okay.
I'm gonna make you get
Okay.
annoyed that you start thinking about it. Yeah.
Okay.
Maybe that means I should explain things worse.
Okay.
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 Maybe we're done.
Okay. That sounds good for today. I'll see you.
Okay, I will stop the recording now.
Okay. Okay.